Welcome to tonight's peaceful journey of scientific discovery. Please settle deeply into your comfortable resting space. Gently close your eyes and breathe very slowly. Let the tensions of the day completely fade away. Tonight we will explore a beautifully hidden realm. We will dive together into the deep and mysterious ocean. This is a completely quiet world of pure eternal darkness. Yet it holds incredible wonders and vast treasures. Our educational focus tonight is deep-sea mining. We will carefully examine various hydrothermal mineral deposits. We will also discuss crucial environmental protection efforts. This documentary series presents 100 fascinating facts. Tonight we will cover the first 10 facts. The deep sea remains our planet's final frontier. Most of this vast space remains entirely unexplored. Ancient minerals lie scattered across the freezing cold mud. Modern robotic technology now allows us to reach them. Let us begin our slow descent into the abyss. Prepare your resting mind for quiet, and fact number 1 begins our journey into ocean history. The complex story of deep-sea mining starts early. It officially started back in 1873. The HMS Challenger sailed across the vast global oceans. This voyage was the first true oceanographic research expedition. Curious scientists dragged a heavy dredge across the seafloor. They pulled up some completely unknown black rocks. Scientists officially named them valuable polymetallic ocean nodules. They first found these strange objects resting in the Kara Sea. Nobody fully understood their true industrial value back then. They sat quietly in museum drawers for many decades. Early human technology could not extract them from the dark abyss. This historical discovery laid the essential groundwork for today. Modern mining engineers now look at these same rocks. Fact number 2 reveals the chemistry of the deep. Polymetallic ocean nodules contain incredibly valuable raw industrial materials. Their unique composition makes them highly desirable for industry. Manganese forms the largest percentage of each individual rock. It often makes up nearly 30% by weight. Iron is the second most abundant chemical element inside. However, the rare trace metals hold the real value. These nodules contain significant amounts of pure valuable nickel. These specific metals are crucial for our modern technology. Electric vehicle batteries require massive amounts of pure cobalt. Wind turbines need copper to conduct electricity very efficiently. Terrestrial land mines are slowly running out of valuable ores. The ocean floor offers a highly concentrated metal alternative. Some deep nodules even contain valuable rare earth elements. Fact number 3 explains their incredibly slow formation process. These metallic nodules grow at an incredibly slow pace. They are among the slowest geological phenomena currently known. A typical ocean nodule grows only millimeters per million years. The formation process requires a tiny central core object. Dissolved metals in seawater slowly precipitate around this core. Layer upon microscopic layer builds up over many millennia. A potato-sized nodule might be 10 million years old. This extreme age means they are a non-renewable resource. Human extraction would permanently remove them from fragile ecosystems. They will certainly not regenerate within typical human time scales. The slow growth depends heavily on specific cold ocean currents. Antarctic bottom water brings crucial oxygen to the dark seafloor. This dissolved oxygen reacts with floating metals in the water. Disturbing fact number 4 introduces the primary global mining location. The most famous mining region is the Clarion-Clipperton Zone. Marine scientists usually refer to it simply as the CCZ. This vast underwater area sits in the central Pacific Ocean. It spans widely between Hawaii and the coast of Mexico. The total area covers roughly 6 million square kilometers. The average cold water depth here measures around 4,000 meters. At this extreme depth, the temperature hovers very near freezing. The crushing pressure is 400 times normal surface level. The dark seafloor consists of soft and sticky abyssal mud. Trillions of valuable nodules rest loosely on this soft mud. Several nations have already claimed large exploration tracts down here. The CCZ remains the primary global target for future mining. Its sheer massive size makes environmental monitoring very extremely difficult. Fact number 5 details the unbelievable wealth of the deep. The total mineral wealth within the CCZ is absolutely staggering. Scientific estimates suggest it holds billions of tons of nodules. There is more valuable cobalt here than on all land. The deep nickel reserves exceed all known terrestrial mine deposits. 21 billion tons of metallic nodules might exist here. This represents a massive financial opportunity for global mining corporations. The total economic value is currently estimated in the trillions. However, extracting them requires highly advanced and expensive robotic technology. Mining companies design massive heavy tracked vehicles for the soft seafloor. They must powerfully pump the heavy rocks to surface ships. This requires lifting material through for vertical kilometers of water. The mechanical engineering challenges are absolutely immense and very costly. The true economic viability of deep-sea mining remains uncertain. Fact number 6 shifts our focus to active underwater volcanoes. Nodules are definitely not the only deep-sea mineral resource. In 1977, marine scientists made a stunning discovery. They were carefully exploring the dark Galapagos Rift ocean zone. They used a famous deep submersible vessel named Alvin. The curious deep-sea researchers found highly active hydrothermal ocean vents. These are essentially boiling underwater hot springs on the seafloor. Cold ocean water seeps deep into cracks in the crust. Hot liquid magma beneath the surface heats this trapped water. The boiling mineral water shoots violently back into the ocean. It carries dissolved heavy minerals from deep inside the earth. This discovery completely revolutionized biology and deep-sea marine geology. These tall mineral towers are extremely rich in heavy metals. The solid ocean crust is constantly recycling and physically changing. Fact number 7 explains how these rich vent minerals accumulate. Minerals from active vents form seafloor massive sulfide ore deposits. Geologists often call them SMS deposits for the sake of brevity. When superheated vent water hits cold ocean water, minerals instantly precipitate. They quickly solidify and slowly fall down to the dark seafloor. Over thousands of years, huge natural mounds of solid ore develop. These dark underwater mounds are incredibly rich in pure copper and gold. SMS deposits are much more concentrated than traditional terrestrial land mines. A single underwater deposit can easily contain millions of tons of ore. They typically form along active mid-ocean ridges and volcanic island arcs. Papua New Guinea was the very first to license SMS ocean mining. The ambitious commercial mining project was officially named Solwara 1. It aimed to mine copper and gold at 1,600 meters deep. Financial and environmental issues eventually stalled the entire Pioneer project. Fact number 8 describes the extreme environment of black smokers. The most dramatic hydrothermal vents are commonly called black smokers. They constantly emit dark, billowing clouds of superheated mineral fluid. The erupting fluid looks exactly like thick black industrial smoke. The physical temperature of this boiling dark liquid is incredibly extreme. It can easily reach up to 400 degrees Celsius. The massive hydrostatic pressure keeps the superheated liquid densely compressed. The dark smoke color comes from suspended iron and sulfide particles. As these heavy particles settle, they build tall vertical chimney structures. Some mineral chimneys grow to be over 18 human stories high. They can rapidly grow several centimeters in a single active day. Eventually, these massive heavy chimneys become structurally unstable and completely collapse. The fallen broken debris creates the massive deep sulfide ore mounds. Mining companies want to harvest these collapsed, completely inactive mineral mounds. Active fact number 9 introduces minerals found on underwater mountain ranges. There is also a third major type of deep-sea mineral resource. These are scientifically known as cobalt-rich ferromanganese ocean crusts. They do not sit on the deep flat abyssal ocean plains. Instead, they slowly form on the steep sides of underwater mountains. These massive submerged volcanic mountains are globally known as ocean seamounts. The mineral crusts tightly coat the hard exposed rock of the seamount. The crust thickness ranges from tiny millimeters to 24 centimeters. They form at much shallower ocean depths than the polymetallic nodules. You can easily find them between 800 and 2,000 meters. These solid crusts contain extremely high and valuable concentrations of cobalt. Mining them presents a very unique and difficult mechanical engineering challenge. Machines must carefully scrape the crust off the hard mountain base rock. The incredibly steep slopes of seamounts make robotic navigation very highly difficult. Scraping fact number 10 covers the international laws governing the deep ocean. The deep ocean requires very strict international legal and environmental governance. The United Nations officially created the International Seabed Authority for this purpose. This governing organization is commonly known around the world as the ISA. It was officially established globally in the year 1994. Its legal mandate covers the seabed entirely beyond any national jurisdictions. This deep area is legally designated as the common heritage of mankind. The ISA must carefully organize and control all mineral-related ocean activities. It currently issues scientific exploration contracts to various participating member states. It has not yet officially permitted any commercial exploitation to actually begin. The organization faces a truly monumental and incredibly difficult political task. It must carefully balance economic development with crucial marine environmental protection. Marine scientists and environmentalists very closely monitor the ongoing ISA meetings. Legal regulations must prevent catastrophic permanent damage to these fragile ecosystems. Fact number 11. Seafloor massive sulfides form near active hydrothermal vents. Superheated water dissolves minerals deep within the crust. This fluid shoots upward through the ocean floor. The fluid temperature can reach 400 degrees. It suddenly meets the freezing deep ocean water. The extreme temperature drop causes a chemical reaction. Dissolved metals quickly precipitate out of the fluid. These falling particles slowly build tall chimney structures. Some chimneys grow up to 40 meters high. Over thousands of years, these structures eventually collapse. The fallen debris creates massive mineral deposits below. These deposits contain vast amounts of valuable metals. Geologists estimate thousands of these sites exist globally. Only a small fraction has been officially mapped. Mining companies view these sites as valuable resources. Extracting them poses significant engineering and environmental challenges. The dark abyss hides these treasures very well. Deep currents slowly scatter the finest mineral dust. The ocean floor quietly accumulates this metallic snow. Scientists study these formations to fact number 12. These sulfide deposits contain extremely high copper concentrations. Land-based copper mines yield very low grades. Most terrestrial ores contain under 1% copper. Deep-sea massive sulfides offer completely different numbers. Some ocean samples reveal up to 15%. This makes them highly attractive to mining corporations. Global demand for copper increases every single year. Electric vehicles require massive amounts of this metal. Renewable energy grids also depend heavily on copper. Finding new sources has become a global priority. The ocean floor holds millions of tons naturally. Extracting this deep copper requires highly specialized equipment. Engineers must design machines for extreme pressure environments. The crushing weight of water complicates every operation. Salt water also causes rapid corrosion of metallic machinery. Companies invest billions to solve these technical problems. The potential financial rewards remain incredibly high today. Yet the true ecological cost remains largely unknown. Scientists urge caution before commercial extraction fully begins. The deep ocean keeps its fact number 13. The Solwara 1 project made deep-sea history. It was the first commercial deep mining license. The site lies in the Bismarck Sea underwater. Papua New Guinea granted this license in 2011. The target area sits 1,600 meters deep. A company called Nautilus Minerals led this venture. They plan to extract massive sulfide deposits here. Engineers built 3 massive robotic mining machines specifically. These machines weighed hundreds of tons each individually. They were designed to cut and crush rock. Pumps would send the slurry up to ships. Environmental groups protested this unprecedented mining operation strongly. They feared irreversible damage to local marine ecosystems. Financial difficulties eventually halted the entire ambitious project. The company filed for bankruptcy in 2019. The robotic machines never mined the actual seafloor. This failure served as a warning to investors. Deep-sea mining remains an incredibly difficult business. The Bismarck Sea vents continue to vent undisturbed. Local marine life survived this fact number 14. Polymetallic nodules grow at incredibly slow geological rates. These potato-sized rocks rest on abyssal plains. They form around a tiny central core object. This core might be a sharp tooth fragment. It could also be a piece of shell. Minerals from seawater slowly precipitate around this core. Manganese and iron oxide form microscopic concentric layers. They grow about 1 millimeter per million years. A single nodule might be 10 million years old. Some larger nodules began forming before dinosaurs existed. They quietly absorb metals from the surrounding water. These rocks contain valuable nickel and rare cobalt. Lithium-ion batteries require these specific rare metals. Mining companies want to harvest them very quickly. Nature took millions of years to build them. A machine could remove them in mere seconds. Once removed, these nodules will not return soon. Their incredibly slow growth makes them non-renewable resources. The abyssal plane would remain permanently altered afterward. Deep sea time moves much. Fact number 15. The Clarion-Clipperton Zone is a vast region. It spans across the central Pacific Ocean floor. The zone covers roughly 6 million square kilometers. This area is wider than the continental United States. It holds the largest known concentration of nodules. Scientists estimate billions of tons rest down there. The water depth averages around 4,000 meters. Complete darkness blankets this massive underwater desert landscape. Temperatures remain just above freezing all year round. The seafloor here consists of soft, sticky mud. Millions of metallic nodules sit on this mud. International contractors have already claimed specific exploration blocks. They send autonomous vehicles to map the terrain. Sonar waves bounce off the metallic rocks continuously. Biologists also study this remote and alien environment. They keep discovering strange new species of animals. Many creatures live directly attached to the nodules. Removing the rocks means removing their only homes. The zone represents a crucial environmental battleground today. Decisions made here will shape fact number 16. Mining machines will stir up massive sediment plumes. Tractors must drive across the soft abyssal mud. Their heavy treads will crush the delicate seafloor. Collecting nodules creates thick clouds of suspended silt. Ocean currents can carry this dust very far. The fine particles might travel for hundreds of miles. This artificial cloud blocks bioluminescent light signals completely. Deep-sea creatures rely on light to communicate. Filter-feeding animals face the greatest immediate danger. Sponges and corals pump water to gather food. The suspended mining dust will clog their filters. These ancient organisms could easily starve to death. The sediment also buries small creatures living nearby. It takes centuries for this dust to settle. The deep ocean lacks strong currents to clear it. Scientists struggle to model these massive underwater clouds. Predicting their exact path remains incredibly difficult today. The environmental impact extends far beyond the mine. One single operation could affect a vast area. The quiet waters would turn fact number 17. Hydrothermal vent ecosystems exhibit incredibly high species endemism. Endemism means a species lives nowhere else globally. A specific snail might exist at one vent. It may never be found at another location. Vent fields are tiny islands in a vast abyss. They are separated by hundreds of miles of darkness. Animals cannot easily migrate between these distant oases. They evolve unique adaptations to their specific chemistry. Some worms thrive in highly acidic local waters. Others tolerate extreme concentrations of toxic heavy metals. Mining a single vent could cause immediate extinction. Destroying the habitat wipes out the entire population. We barely understand these complex localized food webs. New species are discovered on almost every dive. A mining machine might destroy unrecorded genetic miracles. These creatures could hold cures for human diseases. Their unique enzymes might revolutionize modern biochemical engineering. Losing them means losing millions of years of evolution. Conservationists argue for strictly protected marine sanctuary zones. The biological wealth exceeds the fact number 18. The International Seabed Authority regulates deep ocean mining. This organization was established in 1994. Its headquarters are located in Kingston in Jamaica. The United Nations Convention created this governing body. It controls all mineral resources in international waters. These waters belong to the common heritage of mankind. No single nation can claim ownership of them. The authority must balance resource extraction with protection. This dual mandate creates significant internal political tension. They issue exploration contracts to various global nations. Currently they are drafting actual commercial exploitation rules. Many countries demand a pause on all mining. They want more time for detailed environmental research. Other nations push for quick approval of operations. The debates happen in quiet conference rooms annually. The outcomes will affect the deepest places on Earth. Writing laws for the abyss is unprecedented work. Scientists attend these meetings to present new data. They hope biological facts will guide legal frameworks. The fate of the deep sea fact number 19. Valuable cobalt-rich crusts form on underwater mountains. These mountains are known as deep ocean seamounts. They rise thousands of meters above the seafloor. Strong currents sweep across their rocky basalt slopes. These currents prevent soft sediments from settling down. Dissolved metals slowly accumulate on the bare rock. They form a hard pavement of valuable minerals. These crusts grow extremely slowly over millions of years. They are usually just a few centimeters thick. The crusts contain very high concentrations of cobalt. Cobalt is crucial for modern battery storage technology. Mining these seamounts presents unique engineering challenges today. Machines must scrape the crust without cutting rock. Taking too much barren rock ruins the ore grade. Seamounts also host incredibly rich biological underwater communities. Ancient deep water corals grow on these crusts. Some coral colonies are over 4,000 years old. Scraping the crust destroys these ancient fragile forests. Recovery of these ecosystems would take many millennia. The silent mountains hold both fact number 20. Deep sea mining generates intense underwater noise pollution. Sound travels much faster and further in water. It moves 4 times faster than in air. Heavy mining machinery produces continuous low-frequency vibrations. Pumps and cutting wheels create an industrial roar. This mechanical noise can travel for hundreds of kilometers. The deep ocean is naturally a very quiet place. Marine mammals rely entirely on sound to survive. Whales use acoustic signals to navigate the darkness. They sing complex songs to find distant mates. Mining noise masks these crucial biological communication signals. It causes severe stress to deep diving whales. The constant hum disrupts their natural feeding patterns. Fish also suffer from this overwhelming acoustic interference. Even tiny invertebrates show signs of acoustic trauma. Scientists deploy underwater microphones to measure ambient sound. They record the baseline quiet of the abyss. Introducing industrial noise changes the environment completely forever. The dark ocean relies on its peaceful silence. Protecting this silence is vital. Fact number 21 explores seafloor massive sulfide mineral deposits. These rich mineral formations grow around deep ocean hydrothermal vents. Superheated water dissolves heavy metals from the oceanic crust below. The ascending fluid hits near freezing seawater in the ocean. Sudden cooling forces the dissolved minerals to precipitate out immediately. Solid particles fall and accumulate around the vent opening slowly. Over thousands of years, huge chimney structures begin taking shape. These towering chimneys contain dense concentrations of valuable industrial metals. Commercial miners target these specific formations for their copper yields. Zinc and pure gold also exist in high quantities here. A single underwater vent field can hold millions of tons. Geologists map these remote sites using specialized acoustic sonar equipment. They measure the unique magnetic signatures of the sulfide mounds. The total global mineral resource remains largely unmapped even today. Estimates suggest thousands of active vent fields currently exist worldwide. Each discovered site represents a complex and fragile underwater. Fact number 22 highlights the extreme thermal gradients here. Deep hydrothermal vent fluids often exceed 350 degrees. The surrounding deep ocean water remains near 2 degrees Celsius. This massive temperature difference occurs over mere centimeters of space. Extreme thermal shock drives the rapid mineral precipitation process underwater. It also creates unique microhabitats for highly specialized deep life. Some resilient organisms thrive in water near 80 degrees Celsius. Others survive just inches away in freezing ambient ocean currents. Commercial mining operations would inevitably disrupt these delicate thermal boundaries. Heavy industrial machinery alters the natural flow of superheated water. Changing the local fluid dynamics can extinguish a living vent. Without the vital chemical energy, the local food web collapses. Ocean researchers study these thermal gradients using remote-operated vehicles. Specialized titanium probes measure the exact heat signatures of vents. They continuously record temperature fluctuations over long periods of time. These records show highly stable conditions before direct human. Fact number 23 compares marine and terrestrial mineral ores. Seafloor massive sulfides boast incredibly high metal or concentration grades. Traditional terrestrial copper mines often yield under 1% copper. Deep-sea sulfide deposits frequently exceed 10% copper concentration. Some extremely rare samples show copper concentrations reaching 30%. This high material density makes deep ocean mining economically tempting. Gold concentrations also surpass many traditional land-based mining operations. A single extracted ton of seabed ore holds significant value. However, the physical extraction costs remain astronomically high right now. Operating heavy mechanical machinery thousands of meters underwater is difficult. The highly corrosive saltwater environment degrades expensive robotic mining tools. Extreme hydrostatic ocean pressure complicates every phase of the operation. Engineers use advanced metallic alloys to prevent equipment implosions underwater. Surface support naval vessels consume massive amounts of diesel fuel. The overall economic viability fluctuates with global metal market prices. When terrestrial resources naturally deplete, the ocean becomes more. Fact number 24 details the historic Solwara 1 project. This proposed commercial mining site lies in the Bismarck Sea. It sits exactly 1,600 meters below the ocean surface. A private commercial company planned to extract copper and gold. They engineered 3 massive robotic machines for the dark seafloor. The primary bulk cutter machine weighed over 300 tons. It featured huge rotating steel drums covered in metal teeth. These sharp teeth were built to grind massive sulfide chimneys. A secondary collecting machine would gather the crushed mineral slurry. Powerful hydraulic pumps would push the heavy mixture upwards vertically. The ambitious project faced intense opposition from marine conservation groups. Local coastal island communities also protested the planned industrial activity. They deeply feared toxic sediment plumes would ruin local fisheries. Severe global financial difficulties eventually halted the entire mining operation. The company officially filed for bankruptcy in 2019. The heavy robotic mining machines never saw active ocean. Fact number 25 focuses on unique vent endemic species. Many strange animals exist only at specific hydrothermal vent fields. The famous scaly foot snail is a prime biological example. This extremely rare mollusk lives deep in the Indian Ocean. It literally builds its shell using iron sulfides from vents. No other known animal incorporates natural iron into its skeleton. Proposed mining operations directly target the exact habitat it needs. In 2019, scientists declared this unique snail endangered. It was the first marine species threatened by deep mining. Deep vent habitats are geographically isolated like tiny islands underwater. If one specific vent field is destroyed, species cannot migrate. The physical distance to the next active vent is immense. Most benthic bottom organisms travel very slowly across the seafloor. Larval dispersal relies entirely on highly unpredictable deep ocean currents. Marine biologists worry mining could cause immediate species extinction events. We have only discovered a tiny fraction of vent. Fact number 26 concerns the powerful International Seabed Authority. This intergovernmental organization regulates mining in international ocean waters globally. It was established under the global law of the sea. The administrative headquarters is located in Kingston, Jamaica right now. They strictly issue exploration contracts to various nations and companies. Currently, they draft the official mining code for commercial extraction. This legal framework will dictate environmental protection standards underwater forever. Drafting these complex rules requires immense scientific and legal debate. Conservationists argue the current environmental safeguards are completely inadequate today. They demand a total global moratorium on all deep mining. Commercial mining advocates push for swift approval of the regulations. The authority must carefully balance resource extraction with marine preservation. Monitoring strict compliance thousands of meters underwater presents massive challenges. Independent environmental observers cannot easily visit these remote deep sites. The general lack of transparency worries many international environmental organizations. Satellite tracking helps monitor the surface support vessels continuously. Fact number 27 distinguishes between active and inactive vents. Active hydrothermal vents continuously spew hot mineral-rich ocean fluids. They actively support dense communities of unique chemosynthetic marine life. Inactive vents have entirely stopped flowing due to geological shifts. The massive chimney structures remain standing on the cold seafloor. Many commercial mining companies prefer targeting these dormant vent sites. They argue inactive sites have much less biological activity present. Therefore, mining them would theoretically cause less direct ecological damage. However, recent biological surveys challenge this highly convenient corporate assumption. Inactive vents still host highly diverse communities of deep organisms. Deep sponges and cold water corals attach to the chimneys. These slow-growing animals use the tall structures for elevation. Elevation helps them catch passing food particles in deep currents. Destroying inactive chimneys removes crucial hard substrate for benthic life. The deep ocean floor is mostly composed of soft sediment. Hard rock surfaces are rare and highly valuable. For fact number 28 explores the destructive mining plume effect. Seafloor physical excavation creates massive clouds of suspended sediment particles. These dense artificial plumes drift with the deep ocean currents. The fine sediment can travel for dozens of kilometers horizontally. As it slowly settles, it blankets the surrounding benthic habitats. Most deep-sea organisms are not adapted to heavy sediment. Delicate filter-feeding animals easily choke on the thick dust. The abrasive particles clog their delicate feeding and breathing appendages. Furthermore, the crushed or releases toxic heavy metals directly underwater. Dangerous copper and lead dissolve into the surrounding water column. These invisible toxic elements quickly enter the marine food chain. They slowly bioaccumulate in the living tissues of larger predators. Surface mining ships also discharge processed wastewater back into oceans. This creates a dangerous secondary midwater plume of fine particles. Midwater sediment plumes block bioluminescence used by deep-swimming animals. Many pelagic species rely entirely on light signals. For fact number 29 addresses deep-sea industrial acoustic pollution. The deep ocean is naturally a very quiet, undisturbed environment. Acoustic sound travels much faster and further in dense water. Industrial mining machinery generates immense levels of unnatural mechanical noise. Grinding metal teeth create high-frequency underwater acoustic shock waves. Heavy hydraulic pumps produce constant low-frequency structural rumbling sounds. This severe noise pollution completely overwhelms the delicate marine soundscape. Many deep-sea creatures lack traditional visual sensory organs entirely. They navigate and hunt using subtle water vibrations and sounds. Certain whales dive incredibly deep to forage near vent fields. The loud mining noise can severely disorient these marine mammals. It effectively masks the vital acoustic signals used for echolocation. Continuous loud industrial noise causes chronic stress in marine populations. Native fish may abandon their traditional feeding grounds almost entirely. The invisible acoustic footprint of one mine covers huge areas. It extends far beyond the physical boundaries of mineral. Fact number 30 evaluates the ecological recovery time required underwater. Deep hydrothermal vent ecosystems operate on incredibly long time scales. If a fragile vent is destroyed, biological recovery is unlikely. Freezing deep sea temperatures slow down biological growth and reproduction. Deep organisms take many decades to reach full sexual maturity. When mining physically removes the chimney, the entire habitat vanishes. The underlying delicate geothermal plumbing might also be permanently altered. Scientists conducted small-scale seafloor disturbance experiments in the Pacific. They deliberately dragged a heavy plow across a sediment patch. 30 long years later, the tracks remained perfectly visible underwater. The local benthic animal populations had not recovered their numbers. Commercial-scale mining would cause exponentially larger physical destruction overall. The mechanical scars on the seabed will last for millennia. Completely extinct species will never return to the ocean floor. Artificial restoration of deep-sea habitats is practically impossible currently. We simply lack the technology to rebuild complex sulfide. Fact number 31 explains the formation of massive sulfides. These unique deposits form near tectonic plate boundaries. They are born from extreme volcanic heat below. Cold seawater seeps deep into the fractured ocean crust. Magma chambers heat this water to extreme temperatures. The fluid reaches 400 degrees Celsius underground. This superheated water dissolves minerals from surrounding rocks. The enriched fluid shoots back up into the ocean. It hits the near-freezing deep-sea water instantly. Sudden cooling causes dissolved minerals to precipitate out. These falling minerals slowly build towering chimney structures. Over thousands of years, massive mounds accumulate below. These mounds contain highly concentrated metallic ore deposits. Geologists call these structures seafloor massive sulfide deposits. They hold significant commercial interest for mining companies. The mineral density far exceeds most land-based mines. Understanding this process helps scientists locate future sites. Some deposits span hundreds of meters across the seafloor. This continuous geological process forever shapes the fact number 32 details the composition of black smokers. These iconic hydrothermal vents vent dark, mineral-rich fluids. The dark color comes from fine iron sulfide particles. Black smokers host extremely valuable trace metals within. Copper and zinc are the primary targets for extraction. Some chimneys contain up to 10% copper. This grade is much higher than terrestrial copper mines. Precious metals like gold and silver also accumulate here. Gold concentrations can reach 20 grams per ton. The minerals are locked within hard sulfide rock matrices. These machines must grind the solid rock into slurry. The slurry is then pumped to a surface vessel. Engineers face immense challenges designing these extraction tools. The rock is incredibly hard and highly abrasive. Equipment wear and tear happens at an accelerated rate. Maintenance at 3,000 meters deep is virtually impossible. Therefore, durability is the primary concern for mining. Fact number 33 examines the Solwara-1 mining project. This site lies in the Bismarck Sea near Papua New Guinea. It sits at a depth of 1,600 meters. Solwara-1 was the first commercial deep-sea mining attempt. A company called Nautilus Minerals led this pioneering effort. They targeted a rich seafloor massive sulfide deposit. The project gained its initial environmental permit in 2009. Engineers built massive robotic mining machines for this site. These machines weighed hundreds of tons each on land. They were designed to flatten the uneven vent terrain. Another machine would cut the solid sulfide ore apart. A collection machine would gather the crushed rock slurry. However, the project faced severe financial and technical hurdles. Local communities strongly opposed the environmental risks involved. Nautilus Minerals eventually filed for bankruptcy in 2019. The Solwara-1 site remains unmined to this day. This failure highlights the immense difficulty of deep ocean. Fact number 34 explores the ecosystems around active vents. Active hydrothermal vents host vibrant and unique biological communities. These ecosystems do not rely on sunlight for energy. Instead, they depend entirely on a process called chemosynthesis. Specialized bacteria convert toxic vent chemicals into usable food. These bacteria form the foundation of a complex food web. They have no mouth or digestive tract of their own. They rely completely on symbiotic bacteria living inside them. Blind shrimp swarm around the venting hot fluids. Yeti crabs wave their hairy arms to cultivate bacteria. Mining active vents would completely obliterate these fragile ecosystems. The cutting machines would destroy the physical habitat instantly. Changes in fluid flow would starve the remaining organisms. Many scientists argue that active vents must be protected. The biological value far outweighs the potential mineral wealth. These unique life forms might hold medical and genetic. Fact number 35 focuses on inactive hydrothermal vent sites. Because of biological concerns, miners often target inactive vents. These are sites where hydrothermal activity has completely stopped. The magma chamber below has cooled or shifted away. Hot mineral fluids no longer flow from the seafloor. The towering sulfide chimneys slowly collapse over long periods. They form rubble mounds of highly concentrated metal ores. Without the chemical energy, chemosynthetic life quickly dies off. The vibrant tube worms and blind shrimp simply vanish. Mining companies argue these sites have lower environmental impact. They claim extracting minerals here avoids destroying unique life. However, inactive vents are not completely devoid of organisms. Deep sea sponges and cold water corals eventually settle here. These slow-growing marine animals use the hard rock for anchorage. This secondary ecosystem is also incredibly fragile and ancient. Some corals living on these rocks are centuries old. Destroying inactive vents still causes significant ecological. Fact number 36 reveals the difficulty of finding inactive vents. Locating dormant sulfide deposits is a massive technological challenge. Active vents are relatively easy to spot from afar. They emit huge plumes of hot water and chemicals. Sensors can detect these chemical signatures miles away. Inactive vents produce no thermal or chemical signal whatsoever. They are virtually invisible to standard oceanographic scanning equipment. They blend in perfectly with the surrounding dark seafloor. Scientists must rely on advanced high-resolution sonar to find them. Autonomous underwater vehicles slowly map the complex seabed topography. Specialized magnetic sensors also help detect specific mineral concentrations below. Even with advanced technology, discoveries remain incredibly rare. Only a very tiny fraction of the seabed has been surveyed. This scarcity makes each discovered site highly contested territory. Mining companies invest millions just in exploration and mapping. The incredibly high cost of discovery limits rapid industry. Fact number 37 addresses the creation of mining plumes. Cutting solid sulfide rock generates massive amounts of dust. The underwater grinders pulverize the hard mineral structures continuously. This violent process suspends fine particles in the water. Strong ocean currents catch these particles and carry them away. This creates a dense, cloudy plume of suspended sediment. The plume can travel for many kilometers horizontally. It blocks out the faint bioluminescent light of the deep. Deep-sea organisms rely on this light for communication. The thick cloud also clogs the delicate gills of animals. Filter feeders like sponges ingest these sharp, abrasive particles. This causes severe internal damage to their feeding mechanisms. The sediment eventually settles back down onto the seafloor. It buries nearby benthic communities under a thick layer. These organisms cannot survive being smothered by heavy dust. Managing this plume is a major environmental engineering challenge. current technology cannot fully contain the spread. Fact number 38 examines the release of toxic metals. Sulfide minerals contain high concentrations of dangerous heavy metals. These include lead, arsenic, cadmium, and naturally occurring mercury. While locked in solid rock, these elements remain stable. Mining processes break the rock into very fine pieces. This dramatically increases the exposed surface area of the minerals. When exposed to oxygenated seawater, these crushed sulfides oxidize. This chemical reaction releases toxic heavy metals into the water. The dissolved metals spread quickly through the midwater column. They enter the marine food web at the microscopic level. Plankton absorb these toxins directly from the surrounding water. The toxins accumulate in predators higher up the food chain. This process is known scientifically as biological biomagnification. Eventually, these heavy metals could reach human food sources. Commercial fisheries operate in waters above many proposed mining sites. Scientists need decades of research to model these chemical. Fact number 39 highlights the incredibly slow recovery rates. Deep-sea ecosystems operate on vastly different time scales. The freezing temperatures slow down all biological and chemical processes. Organisms grow at a mere fraction of terrestrial rates. Some deep ocean corals grow only millimeters per year. Sponges can take centuries to reach a moderate size. Mining operations completely destroy these fragile deep-sea habitats. The physical rock substrate is permanently removed from the area. Animals have nothing left to anchor themselves onto safely. Recovery does not take years or even a few decades. Scientists estimate recovery could take thousands of years. In many cases, the original ecosystem will never return. The permanent alteration of the seafloor prevents true restoration. The deep ocean offers no such opportunity for human intervention. Once the delicate balance is broken, it remains broken forever. This permanence makes the environmental stakes incredibly. Fact number 40 explains the International Seabed Authority regulations. This organization manages mining in international ocean waters. It was formed under a United Nations Sea Treaty. Its mandate covers all mineral resources in the deep seabed. The authority must balance extraction with strict environmental protection. Contractors must submit detailed environmental impact assessments annually. They must propose strategies to mitigate potential ecological damage. However, drafting exploitation regulations has proven incredibly complex. Member states argue over the acceptable levels of environmental harm. Scientists continuously urge for stricter protective measures and baselines. The authority faces pressure from conservationists and industry leaders. Some nations demand an immediate moratorium on all mining. They argue we lack sufficient scientific data to proceed safely. Other nations push for rapid approval to secure critical metals. The future of the deep ocean rests on these negotiations. The decisions made here will shape marine conservation for centuries. Fact number 41 examines seafloor massive sulfide formation. These massive sulfides form near active hydrothermal vents. Superheated water escapes from the deep ocean crust. The fluid temperature reaches 400 degrees Celsius. It carries dissolved metals from deep volcanic rocks. Cold seawater instantly cools this rising chemical fluid. The sudden temperature drop causes minerals to precipitate. Dark clouds of metal sulfides billow into water. These heavy particles slowly settle onto the seafloor. Over thousands of years, tall mineral chimneys grow. Some mineral structures reach 30 meters in height. These chimneys contain high concentrations of valuable ores. Copper and zinc dominate these deep-sea structures. Mining companies target these massive sulfide ocean deposits. The extraction process destroys the chimney formations entirely. Scientists study these sites to understand mineral creation. The formation process mimics ancient terrestrial geological events. Many land-based mines originated as ancient seafloor vents. Tectonic plates eventually pushed them above sea level. Modern deep-sea vents offer. Fact number 42 discusses the Solwara-1 project. This specific project marked a significant mining milestone. It was the first commercial deep-sea mining attempt. The mining site sits in the remote Bismarck Sea. It lies entirely within Papua New Guinea territorial waters. The target extraction depth was 1,600 meters. A company called Nautilus Minerals led the ambitious project. They planned to extract rich copper and gold ores. Engineers built massive underwater robotic mining machines for this. The project received its environmental permit in 2009. Severe financial troubles eventually halted the entire mining operation. The company filed for bankruptcy in 2019. The specialized underwater robots never deployed to the site. Environmental groups strongly opposed the Solwara-1 mining project. They feared irreversible damage to fragile local marine ecosystems. This high-profile failure served as a warning to industry. Deep-sea mining requires immense initial capital investment. The harsh underwater environment presents extreme engineering challenges. Ocean pressure crushes standard industrial. Fact number 43 explores highly specialized vent endemic species. These unique creatures exist nowhere else on our planet. They rely entirely on chemical energy for daily survival. Sunlight never reaches these extreme and dark ocean depths. Special bacteria perform chemosynthesis to create vital organic matter. This biological process forms the base of the food web. Giant tube worms grow up to 3 meters long. They have no mouth and no internal digestive tract. Symbiotic bacteria live directly inside their long tubular bodies. The scalyfoot snail builds a shell of iron sulfide. Blind yeti crabs harvest bacteria on their hairy claws. These unique animals inhabit very restricted geographical ocean areas. A single active vent field might span just a few acres. Mining operations could wipe out entire localized animal populations. Scientists have identified over 600 distinct vent species. Many more species remain completely unknown to modern science. Tragic extinction could happen before scientific discovery even. Fact number 44 explains deep-sea mining legal regulations. The International Seabed Authority regulates all ocean floor mining. This organization manages valuable resources in international waters. They issue specific exploration contracts for massive sulfide deposits. 7 distinct contracts currently exist for these vent locations. The contracts cover regions on the vast Mid-Atlantic Ridge. 3 contracts focus on the distant southwest Indian Ridge. Each exploration area covers exactly 10,000 square kilometers. Contractors must relinquish portions of this area over time. The authority requires extensive environmental baseline studies from companies. Companies must monitor water currents and local biological communities. The legal framework for actual commercial exploitation remains unfinished. International negotiators meet regularly in Kingston to discuss rules. They debate the environmental regulations for future mineral extraction. Agreeing on acceptable ecological harm levels proves very difficult. Some nations demand an outright ban on all vent mining. Others push for rapid commercial development of deep resources. The authority must balance economic interests with ocean. Fact number 45 describes the danger of sediment plumes. Mining machinery creates enormous clouds of fine underwater dust. These thick sediment plumes pose a severe environmental threat. Cutter heads grind the solid mineral chimneys into rubble. This violent mechanical action releases fine particles into water. Hydraulic pumps transport the mineral slurry to the surface ship. Excess water and sediment get discharged back into the ocean. Deep ocean currents carry these suspended particles for miles. The artificial dust eventually settles over a very wide area. It blankets the surrounding seafloor in thick grey mud. Filter-feeding organisms cannot survive this heavy artificial sediment load. Deep-sea sponges and corals choke on the abrasive particles. Cloudy water blocks bioluminescent communication between deep-sea animals. Toxic heavy metals dissolve into the surrounding ocean water column. Copper and lead concentrations spike near the active mining zone. The long-term effects of this chemical toxicity remain unknown. Scientists use complex computer models to predict plume. Fact number 46 highlights the issue of acoustic pollution. Deep-sea mining generates intense and disruptive acoustic pollution. The ocean depths are naturally very quiet and peaceful environments. Natural sounds include distant earthquakes and occasional whale calls. Heavy mining machinery shatters this ancient and delicate silence. Giant robotic cutters produce low-frequency continuous grinding noises. Hydraulic pumps create a loud and relentless mechanical hum. Sound travels 4 times faster in water than in air. It also travels much further without losing its acoustic energy. The industrial mining noise can propagate for hundreds of kilometers. Deep-diving marine mammals rely on sound for daily hunting. Sperm whales use precise echolocation to find giant deep squid. Beaked whales navigate the dark depths using specialized acoustic signals. Industrial noise completely masks these vital biological communication sounds. It causes severe confusion and stress in marine animal populations. Research shows noise pollution negatively affects deep invertebrate development. Scallop larvae grow abnormally when exposed to loud mechanical. Fact number 47 examines the slow recovery of vent ecosystems. Hydrothermal vent ecosystems recover very slowly from physical disturbance. Active vents constantly rebuild their towering mineral structures naturally. Biological communities can recolonize these active sites relatively quickly. However, inactive dormant vents present a completely different ecological story. Mining companies strongly prefer to target these quiet dormant sites. Inactive chimneys no longer release toxic superheated water into the ocean. This makes commercial extraction much easier and safer for equipment. But dormant vents lack the energy for rapid biological recovery. They host distinct and fragile communities of deep-sea corals. These cold water corals grow just a few millimeters per year. A large deep-sea coral colony might be thousands of years old. A heavy mining machine destroys this ancient growth instantly. Scientific studies show inactive sites might never fully recover. The hard physical substrate is permanently removed by the machines. Without the solid rock, new deep-sea corals cannot attach. The unique dormant vent ecosystem is effectively lost. Fact number 48 details the valuable metals in vent deposits. Vent deposits contain incredibly rich concentrations of industrial metals. Land-based terrestrial mines suffer from steadily declining ore grades. A typical terrestrial copper mine yields under 1% copper. Seafloor massive sulfides offer much higher and richer metal concentrations. Some specific vent deposits contain up to 10% copper. Precious metals also exist in highly profitable commercial quantities. Gold concentrations often exceed 15 grams per metric ton. Silver can easily reach several hundred grams per metric ton. These rare high concentrations attract significant global industrial attention. Technology companies desperately need these metals for green energy solutions. Electric vehicle batteries require massive amounts of high-grade copper. Proponents argue deep-sea mining effectively supports the energy transition. Environmental critics dispute this ecological trade-off entirely and fiercely. They argue terrestrial recycling can meet future global metal demands. The true economic value of vent deposits remains highly uncertain. Deep extraction costs might outweigh the incredibly high ore. Fact number 49 explores the technology of seafloor mining tools. Seafloor mining requires unprecedented and highly advanced engineering technology. Engineers design massive robotic vehicles called heavy benthic crawlers. These enormous machines weigh up to 300 metric tons. They move on wide metal tracks across the soft ocean floor. The primary machine uses a giant and powerful rotating cutter head. It grinds the solid sulfide rock into small manageable fragments. A second robotic machine gathers the crushed mineral ore efficiently. A vertical riser pipe connects the seafloor to the surface. This long transport pipe can be 2,000 meters long. Huge hydraulic pumps push the heavy or slurry steadily upward. The surface support vessel acts as a massive floating factory. It carefully separates the valuable minerals from the salty seawater. Operating these underwater machines requires immense amounts of electrical power. Thick armored cables transmit high-voltage electricity to the seafloor robots. The extreme water pressure demands thick and heavy titanium casings. Electronic components must be completely sealed in oil-filled pressure. Fact number 50 emphasizes the importance of environmental baselines. Establishing deep environmental baselines is critical for true ocean protection. A baseline accurately records the natural state of an ecosystem. Scientists must document the entire area before any mining begins. This crucial task requires years of dedicated deep-sea research. Researchers deploy autonomous underwater vehicles to map the dark seafloor. Sensitive acoustic sensors record the ambient underwater background noise levels. Chemical sensors continuously monitor oxygen and trace heavy metal concentrations. This comprehensive data helps assess the true ecological impact of mining. Without a strict baseline, measuring environmental damage is scientifically impossible. The deep ocean ecosystem remains severely understudied and largely unknown. The precautionary principle guides international environmental policy in this realm. It states that scientific uncertainty should not delay ecological protection. If environmental risks are unknown, industrial activities should be restricted. Conservationists strongly advocate for large and permanent marine protected areas. These sanctuary zones would be permanently closed to all commercial mining. Fact number 51. Examine seafloor massive sulfide deposits. Hydrothermal vents create these valuable massive sulfide deposits. These formations hold high concentrations of precious metals. Superheated water dissolves minerals deep within the ocean crust. The hot fluid erupts into the freezing ocean water. Sudden cooling forces dissolved metals to precipitate rapidly. Particles fall and accumulate around the hydrothermal vent opening. Over thousands of years, massive mineral mounds slowly build. Copper concentrations here can easily reach 30%. Gold and silver also hide within these rocky structures. Terrestrial surface mines rarely offer such high ore grades. A single deep deposit might contain millions of tons. Mining companies view these remote sites with great interest. The metallic deposits often span several hundred meters across. They typically rest at depths of 2,000 meters. Extracting them requires specialized heavy underwater robotic machinery. Engineers design massive robots to cut through solid rock. The extreme water pressure complicates every single mechanical operation. Water pressure here exceeds 2. Fact number 52 describes the iconic black smoker chimneys. Black smokers are the most recognizable hydrothermal vent structures. These towering chimneys emit dark, mineral-rich fluid plumes. The distinctive dark color comes from iron sulfide particles. Temperatures inside the chimney easily reach 400 degrees. The surrounding deep ocean water remains near freezing temperatures. This extreme thermal gradient drives continuous rapid mineral precipitation. Active chimneys can grow up to 30 centimeters daily. Some geological structures eventually reach 60 meters in height. They become highly unstable and collapse under their weight. The fallen rocky debris contributes to the sulfide mound. New mineral chimneys quickly form on the broken foundations. This endless cycle creates dense layers of metallic ore. Scientists first observed black smokers in 1979. The historic discovery happened on the East Pacific Rise. Researchers used the famous submersible Alvin for this dive. They found rock chimneys spewing black fluid like smoke. The structures consist almost entirely of extremely valuable minerals. Mining these brittle chimneys presents unique logistical. Fact number 53 details the ambitious Solwara-1 project. The Solwara-1 project pioneered commercial vent mining attempts. This targeted site lies off the coast of Papua New Guinea. It sits safely 1,600 meters below the ocean surface. A commercial mining company received the first official lease. The groundbreaking agreement was signed in 2011. The primary target was a rich massive sulfide deposit. Engineers built 3 massive underwater robotic mining machines. Each crawling machine weighed over 200 metric tons. One heavy machine was designed to level the seafloor. Another would grind the mineralized rock into small fragments. The third unit would pump the slurry to the surface. Financial difficulties eventually halted the entire deep ocean operation. The ambitious company filed for bankruptcy in 2019. The massive machines never deployed to the actual site. This failure highlighted the severe economic risks of deep mining. Operating in the deep ocean demands enormous financial capital. Maintenance costs for underwater equipment remain exceptionally. Fact number 54 highlights the endangered scalyfoot snail. The scalyfoot snail lives exclusively near active hydrothermal vents. This remarkable creature possesses a unique metallic armor shell. It incorporates ambient iron sulfides directly into its skeleton. The snail absorbs these minerals from the surrounding vent fluid. Its muscular foot features hundreds of hardened iron scales. Marine scientists discovered this unusual species in 2001. They found it thriving in the Indian Ocean vent fields. The snail survives at depths of 2,800 meters. It relies completely on symbiotic internal bacteria for its nutrition. These helpful bacteria live inside a specialized esophageal gland. The unique snail faces severe threats from potential mining. Its entire known habitat covers less than 2 square kilometers. In 2019, its official conservation status changed. The rare species was officially declared as globally endangered. It became the first animal threatened by deep-sea mining. Removing the massive sulfide deposits would completely destroy its home. The heavy snail cannot migrate to other distant. Fact number 55 compares active and inactive hydrothermal vents. Mining regulations clearly distinguish between active and inactive vents. Active vents continuously discharge boiling hot mineral-rich fluids. These dynamic sites support dense communities of specialized life. Inactive hydrothermal vents have stopped flowing almost entirely. The underground thermal energy source has shifted or depleted. Mineral deposition ceases completely when the fluid stops flowing. Many mining companies prefer targeting these inactive sulfide mounds. They argue that mining here causes significantly less biological harm. The dense chemosynthetic biological communities have already died off. However, inactive vents are certainly not biologically barren zones. They host unique assemblages of fragile deep-sea sponges. Cold water corals also settle on the rocky sulfide surfaces. These delicate organisms grow at incredibly slow biological rates. A single deep sponge might live for several centuries. Identifying inactive vents on the dark seafloor is quite difficult. They lack the towering thermal fluid plumes of active sites. Sonar scans often struggle to differentiate them from regular rocks. Geologists must rely heavily on magnetic anomaly. Fact number 56 explores the dangers of sediment plumes. Vent mining generates massive clouds of suspended fine sediment. Heavy underwater machinery crushes the porous sulfide rock structures. This violent grinding process releases millions of microscopic particles. Ocean currents carry this toxic dust across long distances. The thick sediment plume contains heavy metals like lead. Arsenic and mercury also drift through the dark water column. These suspended elements are highly toxic to fragile marine life. Filter-feeding organisms ingest the contaminated floating rock particles. Their delicate feeding apparatus becomes clogged with abrasive rock dust. The dark plume also blocks essential bioluminescent light signals. Many deep-sea creatures rely on glowing signals to mate. Predators use bright light flashes to attract their prey. The cloudy water disrupts these vital visual communication networks. Particles eventually settle back onto the deep ocean floor. This heavy blanket of dust smothers small benthic organisms. A single operation could impact hundreds of square kilometers. Engineers are designing suction systems to capture. Fact number 57 reveals extreme thermal gradients for machinery. Vent environments present extreme temperature gradients for robotic machinery. The erupting vent fluid can reach 400 degrees Celsius. Just 1 meter away, the water is near freezing. This dramatic shift causes severe thermal shock in metals. Mining tools must withstand rapid structural expansion and contraction. Ceramic components often shatter under these fluctuating thermal conditions. Hydraulic fluids behave unpredictably in the freezing ambient water. They become thick and sluggish outside the hot vent stream. If a machine arm enters the hot fluid, seals melt. Engineers must design advanced thermal shielding for sensitive electronics. Powering these massive machines requires thick electrical umbilical cables. These heavy cables connect the seafloor robots to surface vessels. The cables must stretch over 2,000 meters long. They endure immense tension from ocean currents and vessel movement. Supplying megawatts of power through these lines is highly risky. A fact number 58 introduces the International Seabed Authority. This intergovernmental organization strictly regulates deep ocean mineral mining. The authority was officially established in 1994. It manages valuable mineral resources in vast international waters. These deep areas are designated as the common heritage of mankind. Developing a comprehensive mining code has taken decades of negotiation. Drafting effective environmental protection rules is a highly complex task. Scientists demand strict baseline ecological studies before any mining begins. Contractors must prove they can successfully minimize severe ecological damage. The organization has issued 31 exploration contracts so far. Several of these specifically target seafloor massive sulfide deposits. Exploration allows mining companies to map and sample the ore. Commercial extraction requires a separate, much more rigorous exploitation license. No commercial exploitation licenses have been officially granted yet. Environmental groups strongly advocate for a complete global mining moratorium. Fact number 59 explains the impact of underwater noise. Deep-sea mineral mining generates unprecedented levels of underwater noise. The deep ocean depths are naturally very quiet acoustic environments. Sound travels much faster and further in water than air. Rock-cutting machines produce continuous, low-frequency acoustic mechanical vibrations. These loud sounds can travel for hundreds of ocean kilometers. Marine mammals rely heavily on sound for navigation and hunting. Deep-diving whales plunge downward to forage for giant squid. Industrial mining noise can easily disorient these massive marine predators. It masks the subtle acoustic cues they use to communicate. Even small benthic invertebrates suffer from intense acoustic stress. Powerful sound waves can damage the sensory hairs of deep-sea shrimp. These blind shrimp live directly on the hydrothermal vent chimneys. They use delicate sensory organs to detect safe thermal gradients. Vibrations from heavy machinery disrupt their precise spatial awareness. Fact number 60 discusses the slow recovery of ecosystems. Hydrothermal vent biological ecosystems have highly variable natural recovery rates. Active vents might repopulate relatively quickly after a physical disturbance. Microbes multiply rapidly in the hot, mineral-rich fluid streams. Giant tube worms can grow up to 1 meter per year. However, inactive vent communities recover at a truly glacial pace. Once destroyed, the essential rocky habitat is gone permanently. Fragile corals and sponges cannot attach to loose, sandy mud. They absolutely require the solid foundation of the sulfide mounds. Deep-sea corals grow only a few tiny millimeters annually. Replacing a mature coral colony takes many thousands of years. Mining removes the very ground these ancient organisms live on. Scientists conducted a marine disturbance experiment in the Pacific Ocean. They dragged a small metal plow across the deep seafloor. Researchers returned to the exact site 26 years later. The deep plow tracks remained perfectly visible in the mud. Biological recovery in the disturbed area was almost absolute. Fact number 61 details seafloor massive sulfide deposits. These mineral formations grow around deep ocean hydrothermal vents. Superheated water dissolves metals from the ocean crust below. This fluid reaches temperatures of 400 degrees Celsius. The hot fluid hits near freezing seawater upon exiting. Sudden cooling causes dissolved minerals to precipitate out immediately. Tiny particles of metal sulfide fall to the seafloor. Over thousands of years, these particles build towering chimneys. Some chimney structures reach heights of 40 meters tall. They contain high grades of copper, zinc, and gold. Mining companies target these specific sulfide mounds for extraction. The total global mass of these deposits remains unknown. Estimates suggest tens of millions of tons exist underwater. These sites are highly localized compared to nodule fields. A single deposit might cover only a few hectares. Finding these specific deposits requires advanced acoustic sonar mapping. Scientists use autonomous underwater vehicles to locate the chimneys. The extreme pressure makes exploration both difficult. Fact number 62 involves the Solwara-1 project. This site sits in the Bismarck Sea of Papua New Guinea. It was the first commercial deep-sea mining lease. The target depth is 1,600 meters below surface. Nautilus Minerals received the mining lease in 2011. The deposit contains unusually high grades of copper ore. Engineers built massive robotic machines to cut the rock. These seafloor production tools weighed up to 300 tons. The plan involved grinding the sulfide chimneys into slurry. Pumps would push this heavy slurry up a riser pipe. A surface support vessel would then dewar to the mixture. The project faced intense opposition from local coastal communities. Environmentalists worried about toxic sediment plumes reaching shallow waters. Financial difficulties eventually halted the entire Solwara-1 operation. The company filed for bankruptcy in 2019. The giant mining machines were sold off to creditors. This failure served as a warning for fact number 63 highlights unique hydrothermal vent ecosystems. These habitats host creatures found nowhere else on Earth. Giant tube worms grow up to 3 meters long. They have no mouth and no digestive tract whatsoever. Symbiotic bacteria inside their bodies produce food from chemicals. The scaly-foot snail builds a shell of iron sulfide. It is the only known animal to use iron armor. Yeti crabs farm bacteria on their hairy white claws. These animals thrive in highly toxic, heavy metal environments. Mining operations would directly destroy these fragile biological communities. The crushing weight of mining tools obliterates the seafloor. Noise pollution from grinding machines disrupts marine animal communication. Light from submersibles blinds creatures accustomed to total darkness. Many vent species have extremely limited geographic distribution ranges. A single mining site could eradicate an entire species. Biologists argue these genetic resources hold immense medical value. Enzymes from vent bacteria are already used in biotechnology. Losing these organisms means losing potential cures. Fact number 64 examines the International Seabed Authority. This organization regulates mining beyond national maritime boundary limits. The authority was formally established in 1994. Its primary headquarters are located in Kingston, Jamaica today. The agency manages millions of square kilometers of ocean. Drafting regulations for hydrothermal vents proves exceptionally difficult. Active vents are dynamic and constantly changing their shape. A vent can turn off naturally within a decade. The authority must balance resource extraction with environmental preservation. Contractors hold exploration licenses for various mid-ocean ridges. France explores the mid-Atlantic ridge for sulfide deposits. Russia and China also hold contracts in the Atlantic. These exploration zones cover 10,000 square kilometers each. The ISA requires contractors to conduct baseline environmental studies. Scientists must document ocean currents and local marine life. Creating rules for exploitation remains an ongoing, complex process. The mining code has faced numerous delays over years. Legal experts debate how to enforce environmental. Fact number 65 concerns the generation of sediment plumes. Grinding massive sulfide chimneys creates huge clouds of dust. These plumes contain highly toxic heavy metals like lead. Ocean currents carry these suspended particles over long distances. The fine dust clogs the feeding structures of filter feeders. Sponges and corals suffocate under the settling mineral debris. Toxic metals can dissolve back into the surrounding seawater. This contamination enters the deep ocean marine food web. Predators accumulate these toxins in their tissues over time. Return water from surface vessels creates a secondary plume. This midwater plume alters light penetration in the ocean. It disrupts the daily migration of mesopelagic fish species. Scientists use computer models to predict plume dispersal patterns. Field experiments show plumes can travel for many kilometers. The exact settling time of fine particles remains uncertain. Some microscopic dust might stay suspended for several months. Managing these plumes is crucial for reducing environmental damage. Engineers are designing enclosed cutting tools to. Fact number 66 focuses on inactive hydrothermal vents. Mining companies prefer inactive vents over active hot springs. Inactive sites have no extreme heat or acidic water. This makes operating robotic machinery much safer and easier. These dormant chimneys have stopped releasing mineral-rich fluids. For years, scientists assumed inactive vents were biological deserts. Recent deep-sea surveys proved this assumption completely wrong. Dormant chimneys support rich communities of deep-sea corals. Glass sponges anchor themselves to the hard mineral surfaces. These filter feeders require stable rock to grow properly. Inactive vents provide rare hard substrate in muddy abysses. Predatory fish and octopuses use these structures for shelter. Some microbes slowly consume the cooling iron sulfide minerals. Mining inactive vents destroys ancient, slow-growing coral forests. A single deep-sea coral can live 4,000 years. Recovery of these cold water ecosystems takes many millennia. Identifying inactive vents is harder without the thermal signature. Researchers drag sensitive magnetic sensors close to. Fact number 67 details the extreme mineral concentrations. Land-based copper mines suffer from declining ore grades. A typical terrestrial mine yields under 1% copper. Seafloor massive sulfides offer significantly higher metal concentrations overall. Some deep-sea samples contain up to 15% copper. This high grade makes the deposits incredibly valuable financially. The gold content in these chimneys is also remarkable. Certain oceanic deposits hold 20 grams of gold per ton. Terrestrial gold mines often operate with just 1 gram. Zinc concentrations can exceed 20% in some locations. Silver is another precious metal found in the chimneys. These rich grades drive the push for ocean extraction. Companies argue that higher grades mean less wasted rock. They claim deep-sea mining produces a smaller carbon footprint. Extracting these metals requires no terrestrial deforestation or displacement. However, the environmental cost to the ocean is severe. The total volume of seafloor is relatively small. It cannot replace land-based mining. On a fact number 68 explores the extreme thermal gradients. Hydrothermal vents feature the steepest temperature gradients on Earth. The vent fluid exits at 400 degrees Celsius. The surrounding seawater sits at just 2 degrees Celsius. This massive temperature drop occurs over a few centimeters. Deep-sea mining equipment must withstand this thermal shock. Metals expand and contract rapidly in these harsh conditions. Electronic sensors frequently fail due to the intense heat. Hydraulic fluids in robotic arms can boil or freeze. Engineers use specialized titanium alloys to build exploration tools. The thermal energy itself is a massive untapped resource. Some scientists propose harvesting this geothermal heat for power. Thermoelectric generators could convert the temperature difference into electricity. This power could run autonomous monitoring stations for years. It would reduce the need for expensive battery replacements. Currently, the technology remains in the early experimental stages. Mining companies focus solely on the solid mineral wealth. The harsh chemical environment corrodes. Standard industrial fact number 69 addresses the slow ecosystem recovery. Deep ocean environments operate on incredibly slow biological timescales. Cold temperatures reduce the metabolic rates of marine organisms. Growth and reproduction happen much slower than on land. When a vent is destroyed, recovery takes many decades. Scientists monitor sites previously sampled by marine research submersibles. Even small disturbances leave visible scars on the seafloor. Active vents recover slightly faster than inactive dormant ones. The continuous flow of chemicals attracts new microbial life. Tube worm larvae can drift in and settle quickly. However, the original complex biodiversity takes generations to rebuild. Inactive vent ecosystems rely on slow-growing filter feeders. Once a deep-sea coral is crushed, it perishes. The bare rock left behind may never be recolonized. Ocean currents might not bring suitable larvae to the area. Mining removes the very substrate these animals need permanently. The physical habitat is ground up and pumped away. This causes an irreversible loss of the fact number 70 highlights environmental mitigation strategies for mining. Regulators propose establishing networks of protected biological marine areas. These zones would serve as untouched refuges for wildlife. The concept involves creating safety corridors between mining sites. These corridors allow marine species to migrate and reproduce. Scientists map the genetic connectivity between different vent fields. Larvae drift along ocean currents from one vent system. They eventually settle on another vent many miles away. Interrupting this larval highway could cause regional population collapses. The International Seabed Authority requires regional environmental management plans. These plans designate areas of particular environmental interest globally. No mining activities are permitted within these protected zones. The protected areas must match the mined areas environmentally. They must contain similar ecosystems and identical mineral structures. Enforcing these boundaries deep underwater remains a logistical nightmare. Acoustic monitoring stations track the noise of mining vessels. Satellite tracking ensures surface ships stay within designated boundaries. Environmental groups argue these measures are still completely inadequate. They advocate for a total ban on Fact Number 71. Examine seafloor massive sulfide deposits. Seafloor massive sulfide deposits form near active hydrothermal vents. These deposits contain rich concentrations of valuable heavy metals. Superheated water dissolves minerals deep within the ocean crust. The fluid shoots upward through vents into cold seawater. Sudden cooling forces the dissolved minerals to precipitate instantly. Metal particles fall and accumulate around the vent openings. Over thousands of years, tall chimney structures slowly grow. These chimneys can reach 30 meters in total height. Miners target these sites for copper, zinc, and gold. Some samples show copper concentrations above 10%. Terrestrial mines usually yield less than 1% copper. This high ore grade makes vent mining highly attractive. However, active vents support incredibly fragile biological communities. Extracting these minerals would completely destroy the local habitat. Scientists argue for the protection of all active vents. They suggest limiting mining only to dormant chimney sites. Dormant sites lack the intense heat. Fact Number 72 discusses the Solwara-1 mining project. The Solwara-1 project was a pioneering mining attempt. It was located in the Bismarck Sea of Papua New Guinea. The site rests 1,600 meters below the surface. A company called Nautilus Minerals planned to mine sulfides. They received the first deep-sea mining lease in 2011. Engineers built 3 massive robotic machines for this task. The bulk cutter weighed 310 tons. Another machine would gather the crushed ore from the seafloor. Pumps would send the slurry up to a surface vessel. Environmental groups protested this experimental project for many years. They feared irreversible damage to the marine ecosystem. Financial difficulties eventually halted the entire deep mining operation. The company declared bankruptcy in 2019. The robotic machines were never deployed to the seafloor. This failure highlighted the immense economic risks of deep mining. It also gave vent ecosystems a temporary reprieve. Fact Number 73 explains biological chemosynthesis at deep vents. Hydrothermal vent ecosystems rely entirely on biological chemosynthesis. Sunlight cannot penetrate to these extreme deep ocean depths. Photosynthesis is impossible in this absolute, perpetual ocean darkness. Instead, specialized bacteria harness energy from deep chemical reactions. The vent fluid contains high levels of hydrogen sulfide. Yet deep-sea bacteria oxidize this sulfide to produce energy. They use this energy to convert carbon dioxide into sugars. These microbes form the absolute base of the food chain. Many live inside the bodies of larger host animals. Giant tube worms harbor billions of these symbiotic bacteria. The worms have no mouth and no digestive tract. They absorb chemicals directly from the surrounding ocean water. The bacteria feed the tube worms from the inside out. Mining operations would disrupt the flow of these vital chemicals. Without hydrogen sulfide, the entire ecosystem would quickly. Fact number 74 introduces the unique deep Yeti crab. The Yeti crab is a unique resident of hydrothermal vents. Scientists first discovered this creature in 2005. They found it south of Easter Island in the Pacific. The crab lives at depths of 2,200 meters. Its scientific classification name is known as Kiwa hirsuta. The animal lacks functioning eyes due to the darkness. Its most striking feature is its long, hairy claws. These pale bristles are called setae by marine biologists. The setae are densely covered in filamentous chemosynthetic bacteria. The crab carefully waves its arms in the vent fluid. This motion bathes the bacteria in vital chemical nutrients. The crab essentially farms its own food on its arms. Yeti crabs cluster tightly around the warm fluid flows. If they wander too far, the cold water kills them. Mining machinery would easily crush these slow-moving crustaceans. Removing the chimneys would also eliminate their heat source. The Yeti crab perfectly illustrates vent species. Fact number 75 details destructive underwater mining sediment plumes. Deep-sea mining generates massive, destructive underwater sediment plumes. Cutting machines grind the hard seafloor into fine dust. This process releases millions of suspended particles into the water. Ocean currents carry these fine particles over vast distances. The sediment cloud blocks the bioluminescent light of deep creatures. Many deep-sea animals use glowing signals to find mates. The murky water disrupts this vital biological communication process. Furthermore, the drifting sediment eventually settles back to the bottom. This falling dust smothers delicate filter-feeding organisms below. Sponges and corals cannot clear heavy mud from their pores. They slowly starve to death under the artificial blanket. The sediment also carries toxic heavy metals from the crushed ore. These dissolved metals enter the local deep ocean food web. They accumulate in the tissues of surviving marine animals. Scientists struggle to predict the exact spread of these plumes. Deep ocean currents are complex and poorly understood. Fact number 76 highlights high marine species endemism rates. Hydrothermal vents display incredibly high rates of species endemism. An endemic species lives in only one specific geographic location. More than 85% of vent species are endemic. Each vent field hosts its own unique biological community. Some species exist only on a single chimney structure. The distance between active vent fields can be hundreds of miles. The freezing, dark ocean acts as an impassable barrier. Larvae struggle to travel between these isolated thermal oases. This isolation drives rapid and highly specialized evolutionary changes. Scientists discover new species on almost every vent expedition. They have catalogued over 600 unique vent species so far. Mining a single vent field could cause immediate extinctions. We might erase entire species before we even discover them. Genetic resources hidden in these creatures would be lost forever. Some of these genes hold potential for new medical antibiotics. Protecting these sites preserves millions of years of fact number 77 covers the International Seabed Authority organization. The International Seabed Authority regulates all deep ocean mining. This intergovernmental body was established in 1994. Its administrative headquarters are located in Kingston, Jamaica. The authority operates under the United Nations Convention on the Law of the Sea. It manages mineral resources in the International Seabed area. This area covers around 54% of the global ocean. The authority must balance resource exploitation with environmental protection. Currently, they only issue contracts for exploration, not extraction. 31 exploration contracts exist as of 2023. Contractors must submit detailed environmental baseline studies regularly. The authority is currently drafting a comprehensive mining code. This code will dictate the rules for future commercial extraction. Many scientists urge the authority to pause all mining progress. They advocate for a decade-long moratorium on deep-sea extraction. We need more time to study the fragile benthic ecosystems. The final regulations will shape the future of Fact Number 78 explores inactive hydrothermal ocean vent sites. Mining companies increasingly target inactive hydrothermal vent sites. These dormant chimneys no longer emit superheated, mineral-rich fluids. The surrounding water temperature matches the freezing deep ocean. Without hydrogen sulfide, the dense chemosynthetic communities vanish. Miners argue that extracting dormant chimneys causes less biological harm. However, inactive vents are not lifeless underwater deserts. They host unique communities of slow-growing, cold-water organisms. Deep-sea corals attach themselves to the hard sulfide structures. Sponges and anemones colonize the towering, ancient mineral pillars. These creatures grow at incredibly slow rates in the cold. A small deep-sea coral might be thousands of years old. Microbes also slowly weather the dormant sulfide rocks over time. They release iron and sulfur back into the ocean ecosystem. Destroying inactive vents removes essential hard substrate for marine life. Once a dormant chimney is mined, the habitat is gone forever. Recovery of these specific ecosystems would take Fact Number 79 examines intense underwater mining noise pollution. Deep-sea mining generates intense and continuous underwater noise pollution. Sound travels much faster and farther in water than in air. The deep ocean is naturally a very quiet environment. Background noise mostly comes from distant storms or earthquakes. Mining machinery produces very loud, low-frequency mechanical vibrations. Grinding rocks and powerful suction pumps create a constant roar. This noise easily exceeds 150 decibels. The sound waves travel for hundreds of kilometers underwater. Marine mammals rely heavily on sound for navigation and communication. Whales use low-frequency calls to find mates across ocean basins. Mining noise masks these vital biological acoustic signals. It causes severe behavioral changes and chronic stress in cetaceans. Invertebrates also suffer from this intense acoustic disturbance. Loud noises can even damage the sensory organs of fish. The constant hum of surface support vessels adds to the din. A single mining site creates a massive acoustic footprint. This invisible pollution alters the natural rhythm of Fact Number 80 details environmental impact assessment timelines. Environmental impact assessments for deep mining take many years. Scientists must establish a comprehensive baseline of the ecosystem. This requires multiple costly expeditions to the remote ocean site. Researchers deploy sensors to measure ocean currents and water chemistry. They collect thousands of biological samples from the dark seafloor. Sorting and identifying these deep-sea specimens takes thousands of hours. A proper baseline study requires at least 10 years of data. Natural variations in the deep ocean occur over long cycles. Short-term studies cannot capture these slow ecological shifts. Mining companies often rush these assessments to secure their permits. Incomplete data leads to highly inaccurate environmental predictions. Furthermore, testing mitigation strategies at extreme depths is incredibly difficult. Equipment fails frequently under the crushing pressure of the abyss. The lack of sunlight makes continuous visual monitoring impossible. We cannot easily see the damage as it happens below. True environmental oversight remains a massive technological challenge. Protecting the deep requires patience, funding, and fact number 81 details International Seabed Regulations. The International Seabed Authority regulates deep ocean extraction. This global organization formed in 1994. Its main headquarters currently reside in Kingston, Jamaica. They manage all mineral activities beyond national jurisdictions. This vast area covers 54% of oceans. The authority issues specific licenses for exploration contracts. Currently, they oversee 31 distinct exploration areas. Several of these focus on seafloor massive sulfides. These sulfides form around hydrothermal vent chimney systems. Drafting regulations for exploitation remains a complex task. Scientists urge extreme caution regarding commercial mining approval. The authority must balance resource needs with protection. Deep-sea ecosystems remain largely unmapped and misunderstood. Environmental guidelines require extensive baseline biological data collection. Contractors must submit detailed environmental impact assessment reports. These reports evaluate potential risks to benthic life. The regulatory framework undergoes continuous review and revision. Negotiations often involve dozens of member state representatives. Reaching consensus on environmental thresholds takes fact number 82 examines massive sulfide compositions. Hydrothermal vents create rich deposits of valuable metals. Superheated water dissolves minerals from the oceanic crust. This fluid erupts into the freezing seawater above. Sudden cooling forces dissolved metals to precipitate rapidly. These falling particles build towering chimney structures slowly. The resulting mounds contain high concentrations of copper. Zinc also accumulates heavily within these vent structures. Precious metals like gold and silver appear frequently. Some deposits contain rare earth elements in abundance. These elements are crucial for modern electronic devices. A single sulfide mound can weigh millions of tons. The metal grade often exceeds terrestrial mine concentrations. Copper grades can reach 10% by weight. Terrestrial copper mines usually average below 1%. This high yield attracts significant commercial mining interest. Mining companies target these specific mineral-dense zones. Extracting these ores requires specialized deep-water technology. The physical composition makes the rock extremely hard. Crushing this material underwater presents fact number 83 distinguishes between vent types. Miners categorize hydrothermal vents as active or inactive. Active vents continuously spew hot mineral-rich fluids. These active sites host dense communities of life. Giant tube worms and blind shrimp thrive here. Extracting minerals from active vents causes total destruction. Biologists strongly oppose any mining at active sites. Inactive vents have ceased all hydrothermal fluid flow. The chimney structures remain standing on the seafloor. These dormant mounds still contain valuable mineral deposits. Mining companies prefer targeting these inactive sulfide mounds. They believe inactive sites harbor less biological diversity. However, recent studies challenge this specific ecological assumption. Inactive vents support unique assemblages of deep marine life. Sponges and cold water corals colonize the dormant chimneys. These organisms grow incredibly slowly in the dark. They provide essential habitat for deep ocean fish. Identifying inactive vents requires high-resolution sonar mapping. The lack of thermal signatures makes detection difficult. Researchers use autonomous vehicles to fact number 84 covers the Solwara project. This project represented the first commercial vent mine. It sits in the Bismarck Sea near Papua New Guinea. The site lies 1,600 meters below the surface. Developers targeted a massive seafloor sulfide deposit there. The deposit contained exceptionally high grades of copper. Initial surveys estimated 2 million tons of ore. Engineers built 3 massive robotic underwater mining machines. These machines weighed hundreds of tons each individually. They were designed to cut and gather rock. A riser system would pump the slurry upward. A support vessel would process the ore offshore. The project faced intense opposition from local communities. Environmental groups raised concerns about toxic sediment plumes. Financial difficulties eventually halted the entire mining operation. The primary company filed for bankruptcy in 2019. The massive mining machines were sold for scrap. This failure provided a cautionary tale for investors. It highlighted the immense financial risks of deep mining. The ecological impacts of such projects. Fact number 85 introduces the Pompeii worm. This organism lives exclusively on active hydrothermal chimneys. It survives extreme temperature gradients along its body. The worm attaches its tail to the boiling vent. Water at the tail reaches 80 degrees Celsius. Its head rests in much cooler ocean water. The head experiences temperatures around 20 degrees Celsius. This represents the highest thermal tolerance for animals. A specialized fleece of bacteria covers its back. These bacteria provide vital insulation against the heat. They also detoxify heavy metals from the vent fluid. Mining activities would instantly eradicate these fragile worms. The worms cannot survive away from their chimneys. They rely completely on the specific vent chemistry. Scientists study these worms to understand thermal adaptation. Their enzymes remain stable at incredibly high temperatures. These enzymes have potential applications in industrial processes. Destroying their habitat means losing valuable genetic resources. Deep-sea mining threatens countless undiscovered. Fact number 86 explains sediment plume dangers. Mining machinery grinds the seafloor into fine particles. This process generates massive clouds of suspended sediment. Ocean currents carry these dust clouds over vast distances. The plumes can travel tens of kilometers daily. Deep ocean waters naturally have very little suspended matter. Resident organisms are not adapted to cloudy water. Filter-feeding animals easily choke on the thick dust. Sponges and corals cannot clear the settling particles. The sediment buries bottom-dwelling creatures completely alive. These plumes also contain toxic heavy metal compounds. copper and zinc dissolve back into the water column. This toxicity poisons marine life across multiple trophic levels. Midwater ecosystems also suffer from the rising sediment plumes. Bioluminescent fish use light to communicate and hunt. The murky water blocks these crucial light signals entirely. Predators cannot find prey in the artificial fog. Mates cannot locate each other in the darkness. Modeling plume dispersion remains a fact. Number 87 discusses deep sea noise pollution. Seafloor mining generates immense amounts of acoustic noise. Giant robotic cutters grind against solid rock continuously. Heavy pumps transport ore slurries through metal pipes. Support vessels run massive diesel engines at the surface. Sound travels much faster and further in water. Low-frequency noises propagate for hundreds of kilometers. The deep ocean is naturally a very quiet environment. Many marine mammals rely on sound for navigation. Whales use complex vocalizations to communicate across oceans. Mining noise masks these vital biological communication channels. Continuous mechanical roaring causes chronic stress in animals. Fish may abandon their traditional feeding and breeding grounds. Invertebrates also suffer from intense acoustic vibrations nearby. Some cephalopods experience severe tissue damage from loud sounds. Regulators struggle to establish safe noise emission limits. Baseline acoustic data for the deep sea is scarce. Researchers deploy underwater microphones to measure ambient sound. These hydrophones record the natural symphony. Fact number 88 highlights slow ecosystem recovery. Deep sea environments operate at an incredibly slow pace. Temperatures hover just above freezing in most areas. Food resources are naturally scarce in the abyss. These conditions lead to extremely slow biological growth rates. Deep sea corals can live for thousands of years. Sponges take decades to grow just a few centimeters. When mining destroys these communities, recovery takes centuries. Scientists studied experimental mining tracks from the 1980s. After 30 years, the disturbed areas remained completely barren. No new organisms had recolonized the scraped seafloor. The tractor tracks looked as fresh as the first day. This proves that deep sea damage is essentially permanent. Hydrothermal vents are slightly more dynamic than abyssal plains. However, specialized vent species still require specific conditions. Once a chimney is destroyed, the fluid flow changes. The original biological community may never return there. Extinction risks for localized endemic species are very high. Conservationists argue against mining due to this. Fact number 89 details underwater mapping technology. Locating hydrothermal vents requires advanced robotic engineering tools. Autonomous underwater vehicles perform this crucial mapping work. These torpedo-shaped robots swim independently without tethers. They follow pre-programmed grid patterns across the dark seafloor. High-resolution sonar scans the topography for chimney structures. Chemical sensors detect tiny anomalies in the water column. They measure slight increases in temperature and turbidity. These clues point toward hidden active vent fields. The robots dive to depths of 6,000 meters. They can operate continuously for up to 40 hours. Once retrieved, scientists download terabytes of mapping data. This data creates detailed three-dimensional seafloor models. Mining companies use these models to estimate ore reserves. Biologists use them to identify vulnerable marine ecosystems. The technology has revolutionized our understanding of the abyss. We have mapped less than 20% of oceans. These robots accelerate the pace of deep-sea discovery. They reveal a world of fact. Number 90 explores marine protected area strategies. Protecting hydrothermal vents requires establishing strict no-take zones. Marine protected areas prohibit extractive activities like deep mining. These sanctuaries preserve critical habitats and genetic diversity. The Azores created protected areas around their regional vents. Canada established the Endeavour Hydrothermal Vents Marine Protected Area. This was the first protected area of its kind. It safeguards a highly active vent field in the Pacific. Designing effective protected networks is a complex scientific challenge. Vents are naturally isolated and distributed across vast distances. Organisms rely on ocean currents to disperse their larvae. Protected areas must be connected by these larval pathways. If mining occurs between protected zones, connectivity is broken. Species could face localized extinction without genetic exchange. International cooperation is vital for high seas conservation efforts. The United Nations recently agreed on a high seas treaty. This treaty enables the creation of international protected zones. It provides a legal framework for safeguarding deep ecosystems. Balancing mineral extraction with environmental preservation remains fact. Number 91 explores the International Seabed Authority. This organization governs all deep ocean mining activities. The global body was established in 1994. It operates under the United Nations Convention framework. Its main headquarters are located in Kingston, Jamaica. The authority manages mineral resources beyond national jurisdictions. These deep areas cover 54% of global oceans. Drafting exploitation regulations has taken many long years. The mining code remains under intense global negotiation. Scientists urge extreme caution before any mining begins. Current rules only permit exploration of the seabed. Contractors must submit detailed environmental impact assessments first. 31 exploration contracts exist as of 2023. These active contracts cover millions of square kilometers. Balancing resource extraction with environmental protection is difficult. Harmful effects from mining activities must be prevented. Decisions made here will shape the ocean's future. Experts monitor these ongoing negotiations with fact. Number 92 examines regional environmental management plans. These plans protect vulnerable marine ecosystems from mining. Scientists often abbreviate these frameworks simply as REMPs. They establish specific conservation goals for ocean regions. The plans identify areas requiring strict environmental protection. Some designated zones are completely closed to mining. These protected zones maintain essential ecological life processes. Larval dispersal patterns dictate where boundaries are drawn. The first such plan was adopted in 2012. It covered the massive Clarion-Clipperton zone perfectly. New management plans are currently being developed globally. The Mid-Atlantic Ridge is receiving a new management plan. These spatial plans must adapt as new data emerges. Flexibility in management is therefore absolutely crucial now. Scientists update the boundary lines every few years. Monitoring these remote areas requires advanced robotic technology. Only autonomous vehicles can verify. Strict environmental fact number 93 describes areas of particular environmental interest. Scientists call these protected sanctuary regions, APIs for short. 9 such protected areas exist in the Pacific Ocean. They form a massive grid of preserved deep habitats. Each area covers 160,000 square kilometers. The total protected zone is incredibly vast and wide. These zones are strictly off-limits to mining contractors forever. They act as baseline references for ongoing scientific research. Researchers compare these untouched areas with actively mined regions. The central core of each zone is fully protected. A large buffer zone surrounds the central protected core. This buffer prevents drifting sediment plumes from entering inside. The locations were chosen to represent different ocean habitats. These sanctuaries ensure species have safe space to survive. Mining impacts might stretch far beyond the extraction sites. Conservationists argue we need even more protected. Fact number 94 highlights the threat of acoustic pollution. The deep ocean is naturally a very quiet environment. Sound travels very efficiently through cold, dense ocean water. Mining machinery generates intense low-frequency noise continuously underwater. These loud sound waves can travel for hundreds of kilometers. Marine mammals rely entirely on sound for their survival. Whales use acoustics to navigate and find deep food. Mining noise can mask these vital animal communication signals. The background roar of machines causes chronic animal stress. A single mining operation might produce constant mechanical noise. This disruptive noise operates 24 hours every single day. Support vessels on the surface add more engine noise. Multiple mining sites could deafen entire deep ocean basins. Regulations must include strict acoustic emission limits for ships. Engineers are trying to design quieter deep mining equipment. Protecting the acoustic environment is a vital new fact. Number 95 explains the importance of environmental baselines. Establishing environmental baselines is a mandatory first regulatory step. Contractors must study an area thoroughly before mining begins. These complex baseline surveys take many years to complete. Scientists must document every species living down there first. They measure water chemistry and natural ocean sediment flow. This data creates a picture of the untouched environment. Without baselines, measuring future damage is completely mathematically impossible. The deep sea changes very slowly over geological time. Natural variations must be understood before adding human disturbances. Collecting this essential data is incredibly expensive and slow. Many species found during surveys are entirely new discoveries. The authority requires standardized baseline data from every contractor. This ensures different contractors collect comparable environmental scientific information. Transparency in baseline data is vital for ocean conservation. Independent researchers need open access to this critical fact. Number 96 focuses on minimizing harmful sediment plumes. Engineers are developing technology to minimize these sediment plumes. Heavy mining vehicles crawl across the soft abyssal mud. Their heavy mechanical tracks stir up clouds of fine silt. These thick plumes can smother nearby filter-feeding biological organisms. New robotic designs aim to contain this suspended sediment. Suction systems pull the disturbed mud inward almost immediately. The primary goal is to prevent the plume from escaping. Returning wastewater from the surface presents another massive problem. After extracting valuable ores, ships discharge the excess water. Discharging it at the surface blocks vital ocean sunlight. Phytoplankton cannot photosynthesize in murky surface ocean waters. Therefore, regulations suggest deep water discharge systems for ships. Long heavy pipes will carry the wastewater back down deep. Releasing it below the photic zone is much safer. However, deep discharge still creates a large midwater. Fact number 97 discusses the controversy of biodiversity offsets. The concept of biodiversity offsets is currently highly controversial. Terrestrial mining often uses offsets to mitigate habitat damage. A company destroys one habitat but protects another elsewhere. Applying this concept to the deep sea is problematic. Deep sea ecosystems are incredibly unique and highly localized. Hydrothermal vents host strange species found nowhere else globally. You cannot simply offset the destruction of a unique vent. The abyssal plains also have very high local endemism. Endemism means certain species live in one specific place. Restoration of deep sea habitats is practically physically impossible. Manganese nodule fields take millions of years to form. Biological growth rates in the freezing depths are too slow. A disturbed area might never recover its original pristine state. Loss of biodiversity from deep mining will be permanent. We must accept the irreversible nature of this mineral. Fact number 98 reveals discoveries from pre-mining biological surveys. Pre-mining surveys have completely revolutionized our deep biological knowledge. Contractors searching for metals accidentally discover strange new life. These mandatory surveys fund extensive deep ocean biological sampling. Millions of dollars are spent on these remote expeditions. Recent biological surveys in the Pacific yielded amazing results. Researchers found thousands of previously unknown deep animal species. They discovered new types of glowing translucent sea cucumbers. Strange armored crustaceans were found living on metal nodules. Giant single-celled organisms called xenophyrophores were carefully documented there. The sheer volume of new life is absolutely staggering. DNA barcoding helps accurately identify these tiny deep-sea creatures. Many new species are smaller than a few millimeters. This wealth of life complicates the ongoing mining debate. We are discovering ecosystems just as we threaten them. The deep sea is definitely not a barren. Fact number 99 outlines the timeline for commercial mining. The timeline for commercial deep sea mining is approaching rapidly. The International Seabed Authority faces a very strict deadline. A controversial legal loophole was triggered in 2021. This specific regulation is widely known as the 2-year rule. It forced the authority to accelerate its environmental regulations. If rules are unfinished, mining might legally proceed anyway. This prospect alarms many environmental scientists and conservation groups. Several nations have officially called for a precautionary pause. Some countries demand an outright ban on all seabed mining. Meanwhile, mining companies are preparing their massive extraction vessels. The transition to electric vehicles requires vast mineral resources. The tension between conservation and industry is peaking today. Drafting the final global mining code is incredibly complex. The deep sea is the common heritage of all mankind. Profits must be distributed fairly among all global countries. Fact number 100 addresses the ultimate environmental balance. The balance between green energy and ocean health remains unresolved. We desperately need batteries to fight global climate change. Modern batteries require cobalt, nickel, copper, and pure manganese. These essential metals are abundant on the deep ocean floor. Mining the ocean might reduce harmful terrestrial mining impacts. Proponents argue that ocean mining is the lesser evil. However, the deep ocean is our largest global carbon sink. Disturbing the deep sea could disrupt global carbon cycles. The sediment holds millennia of safely sequestered organic carbon. Releasing this carbon could significantly worsen the climate crisis. Furthermore, we cannot easily fix a deeply broken ocean. The deep sea operates on massive geological time scales. Damage done today will last for many human generations. We must weigh the immediate need for metals very carefully. Alternative battery technologies might reduce this massive mineral demand. The deep sea is the final unexplored frontier. We have reached the end of our deep journey. 100 facts about the hidden ocean depths conclude here. We explored the crushing pressure of the abyssal plains. We visited the boiling heat of deep hydrothermal vents. We witnessed strange creatures living in perpetual silent darkness. We learned about the slow growth of mineral nodules. The deep sea is a world of extreme contrasts. It is both incredibly resilient and deeply, profoundly fragile. Humanity is now reaching its mechanical hands far downward. The quest for resources drives us into the dark. Yet, we must remember the value of untouched nature. The ocean provides the clean air we breathe every day. It regulates the temperature of our shared global home. Understanding the deep sea is absolutely vital for our survival. Science shines a small light into the vast abyss. We must protect what we do not fully understand. Thank you for joining this long, peaceful underwater expedition. I hope these facts have brought you deep, peaceful wonder. May your dreams be as deep as the ocean. May your rest be as calm as the abyss. The gentle currents of the deep will continue flowing. They